So now we have a resampler which does the sample rate change into the other direction. We have an input signal with a quite low sampling rate, and now we want to change the sampling rate to a higher sampling rate. So our output signal has a different higher sampling rate, and we can express this relation by a ratio. So here the output sampling frequency is above here, and it is divided by the input sampling frequency. So that's the other way than we had in the downsampling case. Please mind this. And here we also use another symbol. It's not N, it's M, and this is our interpolation factor. So this is the ratio between the output sampling frequency and the input sampling frequency. Yeah, please mind that the sample periods can also be used, but then it is inversed. So yeah, mind that that the output sample period is then here in the denominator. And M is again a natural number, a positive natural number. So our interpolation factor is always an integer value. And yeah, please also mind that here there is a low pass filter too, and here it is always required. And to make an analogy to analog systems, we had the reconstruction. So we had learned in chapter 4 about the inverse process of digital to analog conversion. So we had a digital signal here, and then we reconstructed the analog signal. And this is what happens here in completely the digital domain. So this is again just an analogy to explain it, but here of course we are still at the output, we are still digital, but we can say in a technically and mathematically non-correct sense that this is a digital analog to a digital analog converter or a digital reconstruction. Yeah. So in the analog domain, like in the example of the downsampling, here the analog signal is some kind of sample signal with an indefinite number of samples, where each sample is indefinitely close together and so on. So we here have a sample rate change from some sample rate to sample rate close to infinity. Yeah. And so this is why we can make the analogy to analog systems. But here we are completely in the digital domain. So our resampling increases the sampling rate. And yeah, now we have a look at how this works. So here we have our input signal with a low sampling rate, and the first step is filling here the holes between the samples with zeros. So here we have an upsampling with an interpolation factor of 4. So for each sample we need to add m-1, so in this case 3 zeros in between, equally spaced. And now we have a signal which has a 4 times higher sampling rate. But this signal is not the output of our signal of our upsampler. What follows, and it must follow in in each case, you cannot omit it, is the low-pass filter. And the low-pass filter then reconstructs our signal. So therefore the following filter is also called interpolation filter. And what happens here is, so behind the original input signal, it's some kind of monochromatic signal. And now we have here our zero filled signal, and now our interpolation filter then reconstructs the signal. But in analogy to chapter 4, where we have considered reconstruction of analog signals, the reconstruction does not give us our original signal back. So the process of decimation or downsampling is always lossy. Yeah, so in this case, we can reconstruct the signal because we had a special precondition. The Chenin-Nyquist theorem was fulfilled for the input signal. And so we can reconstruct the signal, the original signal, which is, or a signal which is very close to the original signal. What again here, the part that was depicted with this block diagram was the zero filling the signal, and then by applying the interpolation filter, we do the actual interpolation. Giving us the reconstructed signal. And how does it look in the frequency domain? So here we have the input signal, which has a periodicity of the input sampling frequency. And now we change here in this step by zero filling the signal. We change the sampling frequency, and the resulting spectrum is then periodic by the output sampling rate, or m times the input sample rate. And by zero filling the signal, we still keep this pattern, but we only change the periodicity. So whereas this is one repetition in the input signal, this is one repetition in the zero filled signal. So you see that actually our input spectrum is doubled within one repetition window. Yeah, so here we use an interpolation factor of 2, m equals 2 in this example. Yeah, so it's double here, but it's redundant information, and we want to get rid of this redundant information here. So we apply a low-pass filter or interpolation filter, dotted in blue, and remove the redundant spectral components here, and what we get is this output spectrum. So from this spectrum to this, the periodicity was changed because the sampling frequency changed, but the periodicity does not change between these two steps. What happens here is just applying this filter to get this signal. And yeah, this is our reconstructed signal at the output. And at the last points, we have said that both the interpolation factor and the decimation factor must be must be integer values. So they must be positive natural numbers. But what if we want to change the resampling, the sample rate, for example, by 1.5? So imagine that you have a sample frequency of 1 megasamples, and you want to change this sample rate to 1.5 megasamples per second. So how can you achieve this? It's not impossible, but you need to make a trick, and this is called rational resampling. You just combine a decimator and an interpolator, and then you can determine the total sampling rate by just dividing the interpolation factor by the decimation factor. So you can also change the order. You need to be careful as an engineer to choose the right order, because the decimation step is always lossy, so you will lose information here, which you need to some kind of reconstruct in the interpolator, in the upsampling part here. But because the downsampling step is lossy, you cannot completely reconstruct all the information. So therefore, you might choose this approach. So increasing the sampling rate at first, and then dropping some of the information. So here you add more information to the signal because you increase the sample rate, and then here you destroy some information to get a decimated output signal. But this comes at a drawback that you have a quite huge sampling frequency here. So consider this example. You can achieve this by setting m to 3 and n to 2. So here you have 1 megasample, and here you have only 0.5 megasamples to get 1.5 megasamples here. But here, if you apply the same, then you have 3 megasamples here in the intermediate stage before you can decimate it to 1.5 megasamples. And this can be a problem because you need hardware or software which is able to cope with this high sample rate. So as an engineer, you need to make a trade-off between the approaches here, so to find the right approach. Yeah. And yeah, so this was just to illustrate how rational resampling works. So what was important here in the last 3 videos was the basic theory behind resamplers and how they work and what the consequences are in the time and the frequency domain.